Today we're going to take a look at section 3.2, which is addition and subtraction of whole numbers. We're going to do the addition part today, and we'll save the subtraction part for Wednesday, okay? It divides up pretty nicely that way. All right, so to start with, addition of whole numbers, we have been working with, in Chapter 2, sets. And we talked about this n of A being counting the number of items in set A, n of B is counting the number of items in set B, and if we were to add A plus B together, as long as the sets are disjoint, that matters, then that's the same thing as counting the number of items in their union. A and B are called add-ins, and A plus B is called the sum. So those are pieces of language that even the little bitty ones in school start working with, the words add-ins and the word sums. So you should know those words. All right, so we're going to talk about, or we're going to do an example, and then we're going to talk about different models for addition. So it says we give an example to show why, in the definition of addition, A and B must be disjoint. So what it's asking us to do is to create something that is what? What's it say it's supposed to be? Disjoint. So what are we going to create? Something that what? Well, do we know what the word disjoint means? Maybe I should have started there. Completely separate. Yeah, disjoint means they're completely separate. So what's the opposite of disjoint?
A union.
Well, not that they're a union, but they're somehow joined. So how would that look with sets?
Like the Venn diagram with the circles intersecting.
There'd be something that they cross over and have in common, right? That would be the opposite of being disjoint. Does that make sense? So what we're going to create is we're going to create something that has that property, something that has something in common. Okay? It can be very simple. So we're going to create a set A and set B, and they need to have something in common, because if they have something in common, then they are not disjoint. And what we're going to do is we're going to see that the argument for being disjoint is necessary. Something's going to fall apart when we don't have that condition. All right, so somebody give me some things that A will have in it. Don't go crazy on me. Just a few things is sufficient. Letters, numbers, A, B, C. And we'll use little lowercase letters so that we don't confuse it with our big sets. All right, what about set B?
C, D, and E.
Okay, C, D, and E. So they have something in common, right? Yes. All right, so what is the number of the items in set A? 3. What is the number of items in set B? 3. And if we add these together, what do we get? 6. Okay, coming back over here now. What is A union B? You guys just did a test where you did unions for me. What is A union B here? A, B, C, D, E. And what is the number of items in this union? It's 5. And what do you notice?
In the other addition problem, it doesn't count the C.
Yeah, these are not equal. And the reason they're not equal is because C was counted twice, right? Okay, so that's the argument for why that this needs to be disjoint. It has to be disjoint, otherwise we'll have some double counts in there somehow. Okay, so the sets have to be disjoint in order to be counted that way. So for instance, if we counted my family members, and we counted my husband's family members, somehow that would not work, because those are not disjoint sets, correct? But if we counted my family members and we counted Catherine's family members, then it would work, because those are disjoint sets. Okay, that's what addition does. Addition adds disjoint sets together. All right, so the first thing that we're going to do is we are going to, do I have it here? No, I don't have it here. We'll do it next time. I think it is next time, actually. We're going to talk about 2 models for addition, okay? One model for addition is called the set model, and the set model typically used for whole objects. This is an example. Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? So we can actually draw a picture for this. I mean, that would be one way to do this, would be a concrete picture. And I have colors, so I can even draw them in colors, right? Oh, I should have done blue first, I guess. It says 3 blue crayons. So here's 1, 2, 3 blue crayons. And I have 2 red crayons. And the question is, when I combine them all together, how many crayons do I have? My answer is 5 crayons. Now, it says whole objects here because nobody asked you to measure how long the crayons are, right? It's a crayon. Right? When the kid even, has used it quite a bit and it's kind of down to like half the length, you still call it a crayon. You don't call it half a crayon. Does that make sense? So when we're thinking about sets, we're thinking about things that have whole numbers of objects that we're counting in some fashion. Now that's a little different than over here. This is a number line or a measurement model. So this one's typically used for things that can be partitioned. Joe has 4 feet of wood and 3 feet of aluminum. How many feet of building material does he have? So it's not asking how many objects of building material, right? That'd be 2. He has 2 objects. It's asking how much, in dimensions, a length. How much of a length of this building material does he have? So when we draw this, we would actually have to draw it with some length, and it would have to make sense from a visual perspective. So if you think about it, this is called a number line model because it lends itself nicely to drawing a number line. So the first thing that it said that he had was 4 feet of wood. You can still use colors and you can still draw it in such a way that it makes sense. So here's my wood. If I'm measuring it out, excuse me, I would have from here to here is 1 foot, 2 foot, 3 foot, 4 foot. So here's 4 foot of wood, right? So here it started at 0, 1, 2, 3, and 4. And then it says that he has 3 feet of aluminum. So aluminum is a silver material, and it would be going over here, and we can measure out from here, 1, 2, 3. So if I keep counting up, this would be 5, 6, and 7, and the answer would be that he has 7 feet. But you're counting something different, right? Here you're counting the length of something, whereas in the previous problem you were counting the objects themselves. So you might find yourself thinking, why does it matter? I'm still just adding the 2 numbers together. The reason it matters is this, and it'll come into play more when we do the subtraction and especially the multiplication. If you're working with kids and they're having trouble and you can identify what it is about the problems that's causing them trouble, you're going to be better prepared for being able to fix the problem. So if you could recognize that every single time they have a problem that's about measurement of something, they get it wrong, then you know the problem isn't about adding the numbers. The problem is that they don't know what they're supposed to be adding, right? Okay, so that's the deal. We're trying to figure out, especially when you're talking about real-life application, what is it in the real-life application that's causing the child problems? And if you can specify that it's the type of problem they're working with, then you've kind of solved the first part of the problem. Does that make sense? Okay. Now, there are a couple other terms we're going to look at. The term less than. For any whole numbers, A and B, we say that A is less than B, written as such, A less than sign B, if and only if there exists a natural number K such that A plus K equals B. You may not have thought about it like that, but that's the reality of what it means to be less than. The reason that 1 is less than 5 is because there is some number I can put here and add to the number 1 that will give me 5. That's why it's less than. Okay, and of course that number is 4. Okay, but there's a missing number here that I can put in. That's what makes a value to be less than another one. So thinking about less than in that term, we're going to write a similar definition for less than that doesn't use addition, but it uses subtraction. And when you get to your homework in this particular section, I know that's not going to be till Wednesday or after Wednesday's class, they're going to ask you to do the same thing for a statement about greater than. Your statement is going to look very much like this statement, but the inequalities in the equation are going to look different. Okay? So this says that we're starting out for any whole numbers A and B. We're going to start out that way ourselves for our definition. Okay? So you can write down for any whole numbers the next thing here said, A is less than B, written A less than B. And we're doing a definition again for less than, so that part stays the same as well. Okay, so for any whole numbers A and B, A is less than B, written A less than B. Okay, so all that's the same. You can even put an underline in there if you want to, just like your paper has. The next part said if and only if. That doesn't change either. Okay? If and only if. Oops. There exists a natural number K. We're going to have that part there too. See, like this is not reinventing. Please don't reinvent the wheel. That is not your goal. Your goal is to make as minimal changes as you need to in order to say the different piece that it needs you to. Okay, so if and only if there exists a natural number. Remind me, what is natural? How does natural numbers differ from, say, whole numbers? Good. It does not include 0. So the K value has to be positive, truly positive, right? Can't be 0. There exists a natural number K such that. Now, this is the part that will differ, just the very last piece. Over here, this statement used addition to show that A was less than B. How could I write this statement using A, K, and B to show this with subtraction?
A equals B minus K.
Right, A equals B minus K. And if you think about it, it works, right? 1 is less than 4 because if I take 1 and I take 4, there is a number I can subtract from 4 to give me 1. It's the same argument, but it's an argument made out of subtraction instead of out of addition. All right, so you're going to do a couple things with lesson in this section. And then our last big, I think this is the last component. Oh, second to last. We're almost there. We're going to take a look at today is about whole number properties of addition. All right. So there are 4 basic properties of addition. Some of these properties we will see come up again with subtraction, multiplication, and division. Some hold for all, some hold for one. We're just going to see how it goes. So first thing, closure. If A and B are whole numbers, then A plus B is a whole number. That's called closure. And then the commutatives, also on this slide, it says if A and B are whole numbers, then A plus B is equal to B plus A. So does everybody have those filled in and we can actually talk about them now? So feel free to take notes over what I say because this is all that's written. Closure always feels weird to my students. Okay? The idea of closure is that if you take 2 items from some set, and this one talks about whole numbers, and you add them together because we're working with addition, you get another object in that set. Whole number plus whole number equals whole number. Now you might say, okay, but like obviously that's true. Well, that's unique. That doesn't work for every set. So let me give you an example of a set that it works for that's not whole numbers and a set that it doesn't. Even numbers. Even plus even is even. What about odd numbers? Odd plus odd does not equal odd, right? So this property is very specific. It doesn't work all the time. It also can fail if you switch up the operation. So let's do whole numbers, and we'll talk more about the whole numbers with subtraction next time, but let's see what happens with subtraction. Whole number plus a whole number equals a whole number. But what about a whole number minus a whole number? You could get a negative, right? 5 minus 10, that's a negative number. So it doesn't have to work with all operations either. Whole minus whole doesn't have to be a whole number. Now, could you expand it to include the negative numbers? Sure you could. We could talk about integers. We can say, okay, but if we had integers, positive and negative whole numbers, then we'd be okay with subtraction. And that's true, we would. We would. But would we be okay with division? No. I can divide 2 whole numbers, I can divide 2 integers and end up with fractions, right? Okay, so it matters, 2 things matter in order to decide if something's closed. It matters the sets that you're working with, and it matters the operation that you're working with. So I'd like to give you a visual imagery, or something to visually imagine with closure. We're in a classroom and our door to our classroom is closed, correct? Imagine all of the numbers in whatever set it is. Maybe it's multiples of 7. Okay, multiples of 7, they're floating around in the air. Okay, the door is closed and the operation is addition. If you take two 7, multiples of 7, so like 7 and 21, 35 and 70, whatever they are, and you add those two together, the question is, will that number that you get still be in the room? Because the door's closed. And if it's in the room with us, then the set is closed. If it's not, you would have to open the door, right, in order to find the answer. Now, multiples of 7 work. Whole number of 7, another multiple that's a whole number of 7, those added together give you another multiple of 7. And you're going to be dealing with a lot of multiple kinds of things like that actually in your homework, where they're going to give you a set and they're going to ask, is this set closed? And you have to give the answer, yes or no's. Okay? That, for the moment anyway, does that make sense? Okay. Commutative. Commutative is a property that allows us to change the order of things. Again, you might think, well, yes, 5 plus 3 is equal to 3 plus 5. I've known that forever. Well, that's a really helpful fact. It's a helpful fact in a lot of ways. It's a helpful fact for us right now because if we actually needed to add two numbers together and you have one that's significantly larger than the other one and the child, all they know to do this is counting on their fingers, it's useful because I can take whichever one's bigger and I can add the smaller one to it, right? So it's a useful fact to have, that the order doesn't matter in the addition. The other issue is that, again, this is very specific to the fact that we're dealing with addition and whole numbers, okay? So if I did subtraction, would this work? No, it would not. 5 minus 3 does not equal 3 minus 5, right? So it's very specific to being addition with whole numbers that makes this property actually hold. Two more properties, associative and identity. All right, the associative property says if A and B are whole numbers, then A plus B in parentheses plus C equals A plus, and then the B plus C is in parentheses. And then the second one here is the identity property, and it says there is a unique whole number 0. It's called the additive identity, such that for any whole numbers, or number, excuse me, A plus 0 equals 0 plus A equals A. Okay, let me talk about the associative property first. Sometimes people see parentheses and they automatically think, got to be associative, got some parentheses there, right? The problem is the parentheses can exist when you have other properties present as well. So be careful. What the associative property does is it associates the different values differently. Okay, so associate means the same thing as it does in your real life. Who do you associate with? Who are your friends? Who do you group up with, right? That's what's going on in this particular identity, or this particular property, is it's an association. What's being associated together? So on the left-hand side, it's the A and the B that are associated together, whereas on the right-hand side, it's the B and the C. And you'll remember from order of operations that those parentheses tell you where you start working in a problem. So it's not necessarily intuitive that it should just be able to move parentheses around, because it doesn't always work. And in fact, we'll see, and we'll do it next time, but we'll see that it doesn't work with subtraction. Again, it's unique to addition. It works with addition, it also works with multiplication, but it does not work with subtraction or division. All right, so it matters what you're working with in terms of the operation. Identity property. The identity property has a couple of things in it. Every time I ask a question where I say, what is the identity element? The identity element is the value that makes this work. So what's the identity element that they're referencing in this problem? The magic number here. It's 0, right? 0 is the identity, okay? The property that has to hold for it to be the identity is that when you add it to anything else, that anything else stays the same. Nothing changes. Okay, that's what it takes for it to actually satisfy the requirements for an identity element. Okay, so the identity element is the number 0. The property is that it satisfies that the A plus 0 equals 0 plus A equals A. Okay, so there are two components of what's going on here. Now we're going to have a multiplicative identity. What's the multiplicative identity?
1.
It's 1. It's the number you multiply by that does this too. It's the number 1. So we're going to have a multiplicative identity later. So when we identify that something is the identity, we need to say if it's the additive identity or if it's the multiplicative identity. If you just say identity, you're leaving yourself open to being, less clear than you should. So be careful when you're working with identity that we say additive identity for right now, because that's the only one we have. Let me see if there's anything else that we need to notice. Oh, do notice that this is commutative, right? A plus 0 equals 0 plus A. That matters because subtraction sort of almost has an identity, but it doesn't. You might think, well, it's 0, right? A minus 0 is A. But what happens when you reverse it? You get a negative number. So it has to work in both directions for it to really be the identity. It's almost like if we had something called a half identity, it would work for subtraction. But we don't have such a thing, okay? It's got to work in both directions. So that's a nuance to this particular theorem or property, whatever, that you have to be aware of. All right. Each of the following is an example of one of those whole number properties, and you're going to identify which one it is. So take a minute. I'm going to stop talking. I want you to write down which identity property, which addition property, that's what I meant to say, is present in each of the 4 examples. After you're done, find a neighbor and see what they got. And if you got different things, see if you can figure out which of you has the right one written down. There is one right answer for each one of them, okay? So compare with somebody nearby you. Take about 1 more minute to compare. All right, what did we get for the first one? What do you think, which property is that? That is commutative. Now, I'm going to tell you, this word is like the hardest word in my class for everyone to spell. Not everyone, but it's the word that people spell most frequently incorrectly. It is commutative, not communicative, not communicative. You get all sorts of interesting spellings when people write this one down. It is commutative. It means you commute. Right? So if any of you have parents, or maybe you have before in the past commuted to and from work or school, commute is the basic word you've got going on. What about the second one? Which identity? Ooh, we need the word additive. So jot that down if you missed it. It is the additive identity. It sneaks up on you. Yeah, so there's parentheses though, right? Did that throw anyone? No? Okay, so be careful. Just because you see parentheses does not mean it's associative, right? You've got a 0 on this side and you don't over here. The 0 present doesn't make any difference. It's the additive identity property. How about C? There's not an additive associative. Well, I know what you're saying because this is it. So is it associative or is it commutative?
I put commutative just because the only thing that changed
So the plus 2 is on the outside of both sets of parentheses, right? Yeah. So the only thing that actually changed was the order inside the set of parentheses. So this is actually the commutative property. And the fourth one?
Associative.
That one's associative, yes. Because the value that has or where the location of the parentheses are around the 5 and the 3 is now around the 3 and the 2. That was an unfortunate pause in my writing, wasn't it? Wow. I was just so interested in drawing my arrows. All right. Okay, so we've got the associative property. All right, the last thing that we're going to talk about today is I want to talk about some basic addition and subtraction properties. If you are, wait, no, where did it go? Oh yeah, they're there. Okay. If you are working with small children, these might be helpful to you as they're working and thinking about adding and subtracting. So counting on for addition is one of our basic addition strategies. It is the idea of starting with one value and counting up the additional amount to the other value. All right, so on this one, this is the idea, and kids will often use their fingers, or maybe they'll do tally marks or something like that. So they're doing 5 plus 3, and they say 5, and then they go 6, 7, 8, right? They've counted up from the number that they started with. And they could do it with starting with 3 and counting up to 5, but you usually start with the larger value. So that's a counting up, or counting on is what I meant to say, counting on strategy for addition. Doubles. Has anybody seen doubles used? You have, Rebecca? My son uses doubles. My daughter did too. They definitely teach them. They're not my favorite way of teaching addition, but you'll see them in your books. It's one of the things that's the thing to do these days for whatever reason. So the idea of doing doubles is that the kids learn their doubles first. Okay, so 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4, and so on. And then based on the fact that they know the doubles, then something that is nearly a double can be found easily because they've only memorized doubles, at least to start with. So in other words, if they have 3 plus 4, they think about it as 3 plus 3, which they know, and then they just add 1 to it. Okay? So I'm not asking you to love or to even like particular methods. There will probably be things that you don't like, and that's okay. But what you should recognize is that just because you don't like it doesn't mean that one of your kids might not be able to attach to it and do it a lot better than what you do like. Okay, so keep that in mind. Keep an open mind to the fact that these strategies might be helpful to some of the children that you work with. So this is called doubles. Another method is called making 10. I do this when I shop, actually. I do this a lot. So this is a method for adding to a value of 10 and then including the leftovers. For example, and this looks really bizarre, but pause with me for a moment to think. Instead of thinking of 8 plus 6 and remembering that it's 14, the idea is to think of 8 and figure out what you have to add to 8 to get to 10. Well, you have to add 2. Okay? So from the 6 that you had to add, you've already added 2. So what else do you have to add? 4 more. So the idea is to break apart the 6 into a 2, which I can easily add to 8, and the 4 that's remaining. Okay? This is called making tens. And has anybody seen this one used? Yeah? You do this too? Yeah, I do this when I count in the grocery store. And stuff, I don't quite do it this way. I pair up things that easily make 10 to try and figure out to $1, actually, is what I do it for, right? To kind of approximate what I've got in my cart. Yep. Counting back. So counting back is a subtraction strategy. You start with the higher value and you count back to the lower value. So for instance, if you had like 8 minus 2, you would start with 8 and you go 7, 6, 5, 4, 3, 2, right? And you counted back 6 numbers. So you're starting with the higher one and you're counting back to the lower one. That's a counting back strategy for subtraction. There's also a counting on strategy for subtraction, and it looks just like this one but flipped. You start with the lower value and count up to where the higher value is and figure out how many you counted up to. So we'll do the same number I did. 8 minus 2, so you start with 2 and you go 3, 4, 5, 6, 7, 8, and I counted up 6 values, so 6 is the subtraction value that I would have gotten. Okay, so counting on or counting up from subtraction would be 6 there. Any questions on these? Have you guys seen these used? This is what I remember doing in elementary school myself, actually, is the counting on and the counting back kind of stuff, so it's still used.